Welcome back to Office Hours with Mr. Clark. Today we are going to be looking at periodic trends. Okay, periodic. And also we're going to be talking about metallic bonding. So some periodic trends we're going to be looking at would be atomic size, ionization energy, electron affinity, metallic character. So atomic radius, that's defined as distance from nucleus to outermost shell. We find that with a periodic table. There's a schematic of the periodic table. We find that atomic radius decreases, called AR, decreases. Atomic radius increases. So why is that? So it's due to the phenomenon called effective nuclear charge. Effective nuclear charge. We call that ZEFF. Remember, Z is the symbol for atomic number. And atomic number deals with how many protons we have in the nucleus. So effective nuclear charge is a definition, the attraction felt by electrons in the outer shell from the nucleus. Okay. So there's nuclear charge and then there's shielding. So inner electrons shield outer electrons from nuclear charge. Let's imagine, let's take something like sodium, 11 protons, and it has three shells. One, n equals one, two, and three. So electron in n equals three is shielded by the electrons in shells one and two. So you think of the nuclear charge, the charge minus shielding equals effective nuclear charge. So as we as we go down the periodic table, Okay, go to our table again. There's an increase in shells, thus an increase in shielding. So my Zeph decreases. However, as we go across, Zeph increases. There is there is no ink there's no increase in shells. We're keeping the same number of shells as you go across. Like for example, if I start from sodium, go all the way across to argon, I'm still seeing three shells. Now there are electrons that are filling these shells, but as we go across, electrons in the same shells don't shield as effectively. So even though I'm increasing them with electrons, they're still in the same shells. So there's no increase in shielding as to compared to if I'm increasing the number of shells. However, I am increasing the number of protons as I'm going from, for example, sodium to argon. So therefore, my effective nuclear charge is going to increase. So that explains why as I go down, I'm increasing the number of shells. So I'm making my atoms wider, and I'm also decreasing the effective nuclear charge because I'm having all this shielding, so the atoms, expand in a sense. As I go across, my effective nuclear charge is increasing. My number of shells is not increasing, so my shielding is not as effective as if I'm going down. So therefore, the nuclear power is stronger as we go across the periodic table. That's why the atoms shrink. So you can kind of do a little pictorial there and kind of show. You can kind of see that last one didn't look like it was less, you know. Okay. Now, effective nuclear charge explains other phenomena like ionization energy. Ionization energy, i.e., ionization energy is defined as energy required to take an electron from an atom in its gaseous phase. The energy that takes to remove an electron from an atom in its gaseous phase. Ionization energy, let's see what happens to that. As you go across, i.e., increases. So it's progressively harder to take an electron as you go across the periodic table from left to right, which makes sense because my effective nuclear charge, if you recall, and I'll use a different color here, my effective nuclear charge is also increasing. So I have stronger nuclear attraction as I go across, therefore it's going to be harder to take electrons. The effective nuclear charge decreases as I go down. So what do you think happens with ionization energy as we go down? Yes, ionization energy also decreases because it requires less energy to take as you go down because the effective nuclear charge is less at the bottom compared to the top, so it's easier to pull electrons away. Let's look at electron affinity. Electron affinity is defined as the energy released when an atom gains an electron in its gaseous phase. How does that vary across the periodic table? So what I'm going to do, I'm going to show you how effective nuclear charge varies first. Again, so ZFF, EF, or ZEF decreases as I go down. And it's ZEF increases as I go across. So what do you think happens to electron affinity? Meaning, electron affinity is how strongly atoms can pull in electrons to become ions, to become anions. Let's see. So while you're thinking about it, I'm going to set it up. So EA, as we go across, what do you think happens to EA? Since effective nuclear charge is increasing, I have a much stronger pull from the nucleus as I go across left to right, so EA will also increase. Atoms on the right are more likely to pull electrons in because there's stronger effective nuclear charge. As we go down, what happens to EA? EA also decreases because there's less pulling electrons because we have a lesser effective nuclear charge. So EA and ionization energy, they move the same as you go down and across the periodic table, but for different reasons. Metallic characters. Let's talk about, before we talk about metallic character, well, actually, let's see what happens to metallic character as we go, as we move. So metallic character kind of increases like this. Character. Increases, bottom left is the most metallic, top right is the least metallic. So they're more non-metallic. So what the hell do we expect metallic character? So metallic bonding is a phenomena only experienced in metal. So metals, due to their generally low ionization energy, meaning it's easy for them to lose their outer electrons, when they're in their structures, like a solid piece of metal, like a piece of iron or copper, the electrons from the atoms, the outer electrons, the valence electrons get dislodged, and they kind of they group up, and we call this a sea of electrons that's floating around. And then these metal atoms are now cations because they no longer have their electrons. These electron seas, they electron sea holds plus charges together, like cement in a sense, but also they're responsible for electrical and thermal conductivity. So if you remember, electrical conductivity is results from the flow of electrons. So these electrons can flow when exposed to a potential, and also these electrons can convey heat energy. So that's a metallic character that nonmetals do not have. Also, malleability. These these they're cations now. They can kind of flow very easily over each other, cushioned by these electrons. So we can mold metals when we heat them up. Or even some metals they melt at low temperatures like cadmium. You can mold cadmium in the palm of your hand. Also, ductility. You can stretch into a wire and luster. We can we can that's a sheen. Metals have a sheen that can be we can you can buff a metal into shininess, into a shine. All right. So meaning if you have a ring, like I have a ring on my finger here, um, I can if my ring is a little dull, I can shine it up. And nonmetals, pure nonmetals cannot do that without um, falling apart. Normal metals can be, you can shine metals with a piece of cloth or something, kind of abrasive to get any corrosion or any dirt off. You can't do that with nonmetals. Yeah. So my metallic character increases bottom left, non-metallic character top right. So non-metals are the opposite of metals here. Everything here I have non-metals are opposite. They're not conductive, they're not malleable, they're not ductile, and they don't have luster. Let's talk about ions. Ions, like the size of ions briefly. So cations are smaller than parent atoms. So we think of sodium, for example. Plus, sodium, when it loses, sodium has 11 protons, 11 electrons. Sodium ion is 11 protons, 10 electrons. So we have an increase in effective nuclear charge. I've lost a shell and I've lost an electron, so I have more protons compared to electrons here. So I have a smaller radius compared to this bigger radius. So cations have a higher Zeph than their parent atoms, whereas anions, let's take chlorine, have 17 protons, 17 electrons. Chloride has 18 electrons, 17 protons. So here I have a decrease in Zeph. So I end up with a bigger species. So I have less nuclear attraction, so my electrons kind of puff out and have more electrons. And electrons tend to repel each other once you kind of stuff them into a space. So they want to spread out. So you have a bigger species. So if we rank cations, for example, Na plus, Al3 plus, Mg2 plus, how would I rank these in terms of size? So the question is, which one has the most Zeph? The one with the bigger charge. Why is that? Because aluminum has 13 protons, aluminum ion, but only 10 electrons. So aluminum is going to be the smaller because it has the most protons. It has the highest Zeph. Magnesium, 12 protons, 10 electrons, is next in line. And then sodium is going to be the biggest. 11 protons, 10 electrons. It's the highest Zeph, lowest. So as far as size, increase. Size increases. Aluminum smallest, magnesium middle, and sodium the biggest. if we compare that to, let's look at anions, chloride, sulfide, phosphide, they all isoelectronic, meaning they have the same electronic configuration because they all look like argon as far as electron configuration. 288. So two in the 1s8, two in the first level, uh, eight second level, and eight third level. So n equals 1, 2, 3, right? Because this third level now is filled. So it looks like argon. So chlorine, 17 protons, 18 electrons, sulfur, 16 and 18, and phosphorus, 15 and 18. So the size will increase. In that order because I have in chlorine, I have 17 to 18. And first, I have the biggest ratio of electrons to protons. So my Zeph is lower here. Zeph is higher. So that's how we look at periodic trends. We look at ion size, and really the hero of the story here is effective nuclear charge, or Zeph. All right. Until next time, office hours with Dr. Clark.